Good evening, everyone. Can you confirm if you are able to hear me and the screen is visible? Okay, great. So let's get started. So this is week 6 assignment question discussion. But before we move on to that, any questions from week 5 assessment? I have one request from Anupam. So he says number 5, question 5, 9, and 10. Um, okay, let's see. Anything else apart from that? So, Anupam, have you not received the solution for these week? Okay, I think they haven't given the solution to you.
Answer is C. How it is C, ma'am?
What? Answer is C. Let me check just a second. So this is about this TTC. Okay. No voice. Oh, I wasn't speaking. Are you able to hear me now? Okay, so you want the solution to this. Let's try and solve this. Um,
Ma'am, your voice is not audible. Hello, hello.
yeah, can you hear me?
No, no,
Hello.
no. Voice is not audible.
Okay, give me a second. Can you hear me now at least? Hello.
Ma'am, very low voice.
Can you increase your speaker? Is it the same for others also? Okay, you
Ma'am,
can.
voice audible only.
Okay, Anupam, maybe increase the volume for your speakers. That might help. Okay, let's see. So over here you have this question of trajectory tracking control system for this vehicle. We're minimizing this. And your rolling resistance is PV, the vehicle moves in V velocity. Obviously, the equations are simplified. Given m is equal to this and v is equal to this, find out whether the system is stable in open loop. Okay. So, how did you approach this problem? Tell me, and then we'll see if that is right or wrong. Are you still not able to hear me? So, others who have solved this problem, can you tell me how it was for you? Shrikant and Padmavati, have you solved this problem?
Ma'am, I got the value as -1 and sorry, 510. Ma'am, I will check and see.
Okay.
Ma'am, I don't know the answer is correct or not, but I got the values as -0.5 and 0, ma'am. So I have
Minus
chosen the
zero
answer
point 5 and
1.5
0.
and 0. Oh, nice,
These
ma'am.
are for what?
For lambda values, I got, ma'am. So you said that maximum of lambda 1 and lambda 2, if it is greater than 0, you said unstable. So based on that, I have chosen the answer as stable. But the answer
No,
is
we
marginally
had to
stable.
do maximum of lambda 1 into lambda 2.
Okay, okay, ma'am. So I had thought that lambda 1 and lambda 2, in that, which one is the maximum value, like that I have thought.
Okay.
So
Yeah,
minus,
so for you it was coming as the maximum of this is equal to 0, right?
yes, ma'am.
Then what should be 0? It is marginally stable.
Okay, ma'am. So even if one of the value is 0, so we have to choose it as marginally stable.
N- no, 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 no. The maximum of these two, you took this, right? Like
Yes,
the
ma'am.
maximum of the eigenvalues. What was the maximum of both of them?
Okay, ma'am.
It is 0, right? So if
Yes,
it is
ma'am.
0, it has to be marginally stable, right?
Okay, ma'am. So we should not choose unstable.
You can choose unstable if it is greater than 1. This is going to be unstable. Okay.
Okay,
If it
ma'am.
is less than 1, that is going to be stable. So these were the conditions, I think.
Oh, okay. So in the middle, the value is 0, so it has chosen as marginally stable.
Yeah.
Okay, ma'am.
Okay, so what was the other question that we had to discuss? 5, 9, and 10. So, Anupam, is this question okay with you? Did you also get the same value of these eigenvalues that Padmavati also got? Okay.
5 is clear, ma'am. Now we can start 9 and 10, ma'am.
All right. So, let's see question number 9. Which among the below options are correct combination of these? Discretized series RLC circuit system in question 2. Okay. And discretized trajectory, blah, blah, blah. Stability criterion of open loop system. Okay. Um, so this is question number 9. Let's see what is the thing. Correct combination for discretized series RLC circuit in question 2. So did we have this as discretized or not in question 2? And the other question, discretize the above system. Okay, we had discretized it. And state space we had gotten. So did you try to find out the stability of the RLC circuit in question 2? What was that coming as? We had A and B, so were you able to get the lambda values? And same for question 6. We had these values, right? State transition matrix 1, 0.5. I mean, I think it has changed a bit. So can you just help me with the values that you solved so that I can fix it if possible? So one, like, this is more like a trick, I would say. But if you actually read question number 6, what does it say? It says that your uh, poles are placed at 0.2, right? So even if you don't do anything, since your poles are greater than 2, that is supposed to be unstable, right? And this one, I'm not sure, like, none of you are sharing the answer, but it's fine. Like, even if you take a look at this part is unstable, and there is no option that says that the other one is unstable and the first one is stable or marginally stable or so on. So the only option that is right is this one, right? If I just look at the question and don't do any kind of solution or anything, then this is the answer. But there should be the correct way of doing it, like you would have done. You would have gotten the state transition matrix, then you would have gotten the roots out of it, like the eigenvalues, and then gotten the maximum eigenvalue values. So is this question fine? Okay, let's move on to the next question. So the last question is more of a true false. It says find whether the following statements are true or false. So it is saying that in the absence of this rolling resistance, the trajectory tracking open loop resembles the series RLC circuit system. And in the absence of the string, a spring mass damper system resembles the trajectory tracking system, and this past control input is considered as another in delay aware system design. So this was anyways true, and that we had discussed because all the options are anyways fine. But if you actually look at mm, their systems, like let's say if I look at this question, okay, so if I go back here, and for the rolling resistance, which is B, right? I think the rolling resistance, the vehicle faces a backward. So that is your B. So if you put B is equal to 0, which is over here if I put it as 0, right? So does that resemble this one? Like this question that we had solved over here. So what was the A over here? Can you tell me? This was from the PDF that I had shared in the last class. Can you please share that? What was the value you got for A? See, either paste that in the chat window or like unmute yourself and speak. Otherwise, I won't be able to help you with this question.
Ma'am, you're asking for first question, ma'am.
Yes, I'm asking for the first question that what was the value of A that you got? Which option is correct over here? Tell me.
Ma'am, D option, ma'am. As you have shared that PDF with that, I can
Mm-hmm.
able to share this, ma'am.
Okay, you were able to solve this, right?
Ah, yes, ma'am.
Okay, great. So over here, our A is minus 1, 1 and 0. Okay, let me just write it over there itself. So question number 10. In this, for the RLC circuit, your A is equal to what? Minus 1, minus 1, 1, 0. Your B is 1 and 0. C is 0 and 1. And your du is equal to 0, right? So this is your RLC circuit system. And in the second one, it says that in the absence of rolling resistance, the trajectory tracking open loop resembles this one. So let's see what is the thing for trajectory tracking system. So what was the value of A that you got over there? A, B, C, and D for the trajectory tracking. Question number 5. So it was 0, 0, 1 and B by M, right? Minus B by M. And then what was your B? Your B by 0 and 1 by M. And then your C was 1, 0. And then your D was 0, right? So over here, if you just swap x1 and x2, you actually get what? 0 minus B by M, 0 and 1. Your B becomes 1 by M and 0. Your C is 0 and 1. And then D is 0. So this to this, what have I done? I have swapped x1 and x2. Okay. So this says in the absence of rolling resistance, which is B. So let's say if this one is your 0. Okay. Um, so in that case, most these resemble, but this does not. Hmm, Yeah, the trajectory tracking open loop. And is this the closed loop? I guess. No, this is also for the open loop only. So yeah, this is a bit tricky. You will have to check with NPTEL for the exact answer because I don't see a resemblance over here. And the answer, what is the answer that has been provided? The answer is C, right? Okay, if the answer is C, then this option is correct anyways. So these are not resembling, right? These two. So this is false, the first statement. What is the second one? In the absence of spring, a spring mass damper system resembles the trajectory tracking system. Okay. So the spring mass damper system we covered in which one? Week 4. Let's see, not this. So this is the spring mass damper system, right? What was my A over here? Either of these, correct? State transition matrix. This is your A or B, right? Minus B by M, minus K by M, 1 and 0. Let's see. So I'll just copy. So your spring mass, what is it? A is equal to minus B by M minus K by M, 1 and 0. Okay. And then 1 by M and 0. Your B is 1 by M and 0. What is it trying to resemble? Resembles the trajectory tracking system. So your trajectory tracking is over here. Yeah, so this is also like 0, 0, 1 and minus B by M, right? And B is equal to 1 by M by 0, right? Here I have swapped, so let me swap it again. It is actually this 0, 0. I think you can swap it like this probably. 0, 1, 0 minus B by M. 0, 1. This should be 0 minus B by M, 0 and 1. This part resembles fully, but this one we'll have to check like in detail. Okay, let's see. So over here, if I'm doing this input to state transition matrix, so if I have x1 and x2, what was the option? So if you have x1 dot and x2 dot, it is 0, 1 minus k by m minus b by m, right? So it is, wait, 0, 1 minus k by m and minus b by m, right? And then this is 0 and 1 by m. Okay. So now if you try to resemble this from the earlier one, right, in the absence of the spring, So if your spring is not there, so spring has this spring constant of K, right? And the damper is having this coefficient of B, right? So if you tell that the spring is not there, what is going to happen? You will have 0, 1, 0 and minus B by M, right? And your B is equal to 0 and 1 by M, right? So this part and this one is actually similar, right? So if I don't swap x1 and x2 over here, I thought if we try and change and it might resemble, but it's not resembling, so no point doing that. So if you try and check the state space matrices for these two, RLC circuit and trajectory tracking, it's actually not similar. But if you just check this trajectory tracking and spring mass, when your K is equal to 0, these two are similar, right? This and this are similar. So the second option is true. So it is false, true, and true. Is this clear?
Yes, ma'am.
Okay, great. So should we move ahead to week 6 assignment? I think I would start with the questions itself because they are this week's theory was pretty easy. So we can directly jump to the assignments. Let me know. Okay, so let's get started with this. So this week, in general, I would just tell the topic. It was about this um, hybrid automata based modeling of CPS. So in general, this deals with your finite state machines and all of that. So you would know that if you are in this state and you take some action, what happens, and those things, right? So let's go through that. um, so in general, all the questions are very intuitive. If you actually try and work through it, I'm sure you all of you would get 100% in this assignment. Okay, so let's see. Consider below vending machine finite automation. The operator dot stands for concatenation of events, plus means choice between the events, and star indicates any finite number of repetitions for an event or string of events. So before asking this, have you heard about this AND operation and OR operation in digital electronics?
Yes.
Okay, so AND operation is A dot B, right? Which means that either one of them is 1, like if only with if both of them is 1, it's equal to 1. So that is like concatenation of event. OR is like A plus B, correct? So even if one of them is 1, your answer is 1, like your output is 1. So that's what here the plus means choice between events. So you can choose either of them. Okay, and this star indicates any finite number of repetitions. So this is like unique to this. So the question says, which of the following expressions characterizes the language accepted by the vending machine? Okay, so how are you going to represent it? This is, let's say, user over here. All right, the user sends, like user, you start with state q naught. So all of these circles, they are actually showing a state. Okay, these are the states. And these are actually the different actions. Okay, or, and these are basically your choices. So now, if you are in q naught, and you put a coin inside your vending machine, what happens? You go to a state called Q1 from where you have two choices, right? So once you insert the coin to the vending machine, the machine asks you, which product do you want to buy? Then the options that are displayed are Coke and Pepsi. There is no other option for you. You will choose either of them, right? So you choose either of them. And once you just enter it, it gets dispatched. When you pick it up, it goes back to the initial state that you were in. And you can do this unlimited number of times. So this entire loop, let's say this you did once, this you did for the other time. So this can keep on going on, right? Like this is like infinite. So star actually indicates any finite number of repetitions for an event or a string of events. So whatever you have inside your equation, you are going to put the star, okay, which means that that is going to happen for finite number of repetitions. All right. And you have to tell the steps. So it's basically this q naught dot, actually q1 dot q2. I mean, I won't even say q2, right? So yeah, it's more about you have these two options. So inside this there can be two options, right? So it can be that your coin is there, and then you take the Coke, and then you have the taken, okay? Or you will have the coin, and then you take a Pepsi, you select a Pepsi, and then you go to the taken. So both of them can be there. So how are you going to present it in the format that these options require? I think you should be able to do that. Is that okay? Let me know if this is clear. We can then move on to the next question. Okay, since there are no questions. Okay, so this is the second question. All right. Now over here, you have to consider a semi-automatic transmission system in a car. The gear transmission can be done either manually as per the driver's will or automatically as per the car's will. So you have two options over here, okay, manually or automatic. Now, if the angular velocity crosses certain threshold, the automatic transmission takes prominence. Okay, so if your omega is greater than omega I, your ith gear is activated from I minus 1th gear. And if omega is less than wi, this gear is activated from the ith gear. All right. Now the state dynamics of the ith gear is as follows. So this is omega naught is equal to nu iwu, where ni is the gear ratio for this gear. U belongs to -1 to 1, which is your throttle, and D is equal to up comma down is the driver's input. Okay. Also the position is given by theta. So the diagram below represents the hybrid automata to model the system. So over here your theta dot is equal to omega, that we know, and omega naught is actually angular acceleration, right? And that is represented using this formula, eta 1 into omega into u. Okay. So now if the driver says up, or like from here you were in um, state 1, let's say state 0. So you go to this state. Okay. Now over here your theta dot is w and your omega naught is this. Omega dot is this, right? So d is equal to up, again you go to the next state, and d is equal to down. So you go back to this one. D is equal to down, you go back to this one, and d is equal to down, you go back to this one, right? So Hmm. Actually, this is a bit confusing. It is 1, 2, 3, 4, 5, and 6. All right. So the guard conditions eligible for automated transmission are labeled with numbers. Okay, these are your guard conditions. Okay, and then some guard conditions are provided below that should match the labels. So choose the matching numbers. Okay, so we have these some of these guard conditions. Let's see. So if we want to have automated upshifting and downshifting, right? So if your omega is greater than omega I, what is the question actually? Let's focus on this part. Omega greater than omega I. And ith gear is activated from I minus 1th gear, right? And omega is less than omega I minus 1th gear is activated from ith gear, right? So let's see over here. Let's just pick one of them. Maybe I would start with this, or whatever it is. Let's say omega greater than omega 2. So now over here, what happens is, mm, if your omega is greater than omega 2, you actually mm, let me just try and arrange this. I think this is a bit weird. Okay. So your omega is greater than equal to omega 2. You have omega less than omega 2, right? And you have these two. So you can pair up these things. Okay, let's see. I'll try to help you out. So now omega is like this. Okay. Now over here, they should actually have put omega 1, omega 2, omega 3 like that. Something like that they should have done. Okay. So now let's say if your omega is less than omega 2, which means let's say over here you have some kind of omega, right? And if your omega is greater than omega 2, you go to this one. And if it is less than omega 2, you go back to this one, right? So this is maybe let's say for E and this is for F. Now over here, this is omega greater than omega 3. So this is for your C and this is actually for your D. Next is actually omega greater than equal to omega 4, which is A, and you go back, which is your B. So you can just choose those specific numbers, which are the guard conditions, and you can just try and solve this question based on that. Okay. So I hope this is clear. Any questions? Okay, no questions. State whether the following statements are true or false for HA tuple QXF init inf EGR. Okay, so how many of you have watched the lectures? Can you raise your hand? Nice. Padmavati has watched the lectures. Okay, great. So you can lower your hand. So can you tell me, okay, so Anupam has also done. Nice. So can you tell me exactly which slide has the answer to this particular question? So there is one particular slide, right, which defines all these variables which are there. So you just have to check the definitions. So, uh, yeah, I guess HA formal definition, and this is also HA tuple. So you have your tuple over here, right? This is exactly the same what is being asked over here. QXF init in EGR. You have QXF init in EGR, and they actually represent what is over here and over here. Okay, so you can actually go to, which is this slide number 15. So if you refer that slide, it should be good. All right. Let's move to the next question. Again, a simple matching statement of a theory type question. So match the following statements or notations for a hybrid automation H. Okay. So these are more from, again, from the same theory. So you, if you would have gone through the, I would say, the lecture, you should be able to just do it. So you can move around different slides and you can check. All right. So let's say if you have that all possible executions of H starting from Q naught to X naught, what is that thing called as? So you can check, let me just see, executions, right? Hmm. Yeah, executions is over here. Okay, so you can just check the semantics and everything. And there is an example also in the end. Yeah, so these things. So basically slide number 30 and 31 should give you the answer to this particular question. Okay, so let's say if I just go through one of them, subset of executions that are finite and terminate after some time. So which is them? Mm-mm-mm. Finite executions with initial conditions. And do we have anything? E H star Q naught X naught. Right, so somehow things like that you can just work around. So all of these are over here um, in this. So there is this EH infinity, EH star, EHM, and EH. And what all is EHM, EH star, and EH infinity. So all four are there in this slide. Okay. The next two, like non-blocking and deterministic, those two are on slide 31. All right. So you can just go through the definitions and you can solve this particular question. Okay. So I'll move on to the next one. Okay. So the next question says, consider the following HA. HA is your hybrid automata. So now let's say y is equal to 1. And then you have one state over here. Then what is y is equal to 10 and x, this equation? These are some conditions, right? So this is your guard condition. I think guard condition or guard variable, something like that it is called as. Yeah, guard condition. And then these is actually your reset map. Okay. So what does the question say? First of all, let's understand this. So over here, when you have y is equal to 1, you can move to this state where your x dot is equal to 1, y dot is equal to 1. You are in L naught state and your y is less than equal to 10. Right? Now, if your y is equal to 10 and if your x is equal to 0, then you reset your map, right? And then you are at L1. So this is your flow. Now, following the notations that we learned in this course, which of the following denotes R and G? So first of all, let's understand what are these R and G. So R is actually your reset map. Okay. And your G is actually your guard condition, right? So now, what is this question asking for? This question is asking for R of L0, L1, and X. What does this mean? This is actually the reset map while you transition from location or state, either of that, right? L0 to L1, right? That is x is equal to 0. So over here you will have to check that what is your reset map when you transition from L0 to L1 and your x is 0 because you're resetting on x, right? So that is happening over here, correct? That is one, it is happening over here, one it is happening over here. In this case you are transitioning from L0 to L1. In this case you are transitioning from L2 to L3. So this is not the correct one. You have to check for this particular transition specifically. All right. So in that case, your this R part, you will have to check over here that what is the correct option for that. What is the second thing? Guard condition of L0 to L1. So what does this mean? G of L0 and L1. This actually means your guard condition, which is what is the value of y when transitioning from L0 to L1. Okay, so I hope you'll be able to answer this question. Okay. Yeah, this is pretty easy. Let me know if I can move on to the next question.
Yes, ma'am.
Okay. Okay, so another question is from the same one. For the automata that is shown in question 5, what should be the state when y is equal to 8 and x is equal to 4? Okay, so let's see. If your y is equal to 8, first of all, then you are over here, right? Or maybe let's just count that. Okay. Mm, x is equal to 4. So over here you have a reset, right? And then here you have 2. And then over here you again have a reset and then you have 2. So at any point of time, even if your x is becoming as 4, hmm, so when y is equal to 8, there is no transition, right? There is no transition as such. And you are over here, let's say. And your y is how much? 1, 10.
X is always what say 2 now.
What?
X is always less than equal to 2. How we are going to x is equal to 4?
No, x can it's more about it can increase, right? So your time is elapsing. So whenever you reset, let's say over here you have reset, right? And over here you stayed for 2 units of time. So at x is equal to 2, you changed your state, but over here you stay for more units of time. Um, give me like let me think for this specific thing. Like how do we get that? So So when your y is equal to 8, you are actually over here only. You never increased, right? So I think using that
I
only you
think
can give the
L2 is the
answer.
answer.
Mm-hmm.
L2 is the answer. I'm correct.
Hmm. Mm. Give me a moment. You're saying A is the right answer? So y is equal to 8, there is no transition, right? So at least let's keep that. But at x is equal to 4, which means that mm, I think that is also a non-transition. So these both are not transitioning anywhere, right? Yeah, you actually have to just figure out that which state are you going to be in if you are having these values. So yeah, I guess it could be L2, but yeah, you could be at L2. But see that if you are saying that you are at L2, right? Your y is equal to 10 over here, and your x is equal to 2, right? And but even if you are trying to transition over here, but your y should be equal to 5, so you cannot be at L2. This is at least my understanding. So maybe work around this and see what is the best fit for these two values of y and x. So how much time are you spending in each of these states? Can you tell me? So in L1, in L0, for how many units of time are you spending, like, are you staying in that particular state?
So in L0, at least 10 units of time. L0.
Okay, 10 units of time. Hmm. And then what about L1?
2 units.
Okay.
2.
What about this? So what you can do is, instead of doing all of this also, just I would still say that check the values of these, like, transition conditions and all this. This is a very straight question. I think you should be able to do it. So don't worry about that. I think the other one is probably tricky. So let's see. Here you have y is equal to 3 and x is equal to 1, right? So again, it's the same thing. So for y is equal to 3 and x is equal to 1, so your y is equal to 10 already over here. I think both of them is like a lesser value of x only. Yeah. This one satisfies y less than 10 for both of them, right? And over here y has to be greater than equal to 5, and these two are there. So yeah, I think you can answer that one also. That one is also pretty easy. Now the last question says, for the HA model in question 5, can there be a run such that y is equal to 14 or y is equal to 0? Okay. So if you have y is equal to 10, you spend 2 units of time in this particular one, you get like what? Y is equal to, so you are increasing, right? So 10 was your initial, plus if you stay for 2 units of time, 2 into 1, right, which is 12. 2 into 1 y, because your y dot is equal to 1. Okay, so your y becomes 12 over here, and then let's say you transition, and then what is your y value? Let's say over here you stay for how much unit of time? Let's say again, like let's say 2 units or so, right? Or maybe 1 unit. Okay, so in L2, if you spend 1 unit of time, so you have 12 plus 1 unit into minus 2, right? So this is actually 10, but you can transition only at y is equal to 5, right? So you will have to spend how much amount of time? After how much will this become 5? So I think maybe 3 or 4 seconds or so, right? So you will have to just think about that. But you understand this calculation, right? How you get the values of y and the values of x also, right? So whatever amount of time you spend in each of these, you are going to just add the initial value plus units of time into the x dot and y dot that you have. Okay, and every time your x dot is equal to like 1 only, so whatever units of time you have, you just add that much units of time to your x. But you have to be careful about calculation of y dot. Okay, so you will have to make some calculations like this. Is this okay?
Yes.
Okay, nice. So I think this this week was pretty easy. But try to solve this properly and understand these questions. These are more of mathematics, so should be fine with all of you. So if there are anything that I should like explain in detail because you have time, so let me know if I should explain something more in detail, or we can wrap up the session now itself because there were only 8 questions, and we also discussed the last week assignment questions. I'll wait for a couple of minutes. You can let me know. All right, so if there are no more questions, we can wrap up the session, and I'll be around until 8 p.m. So you can always join back and ask me questions. So Yeah, thanks for attending the session. We'll meet next Saturday, 6 p.m. again.